Hey class, this is Mr. Roberts, and we're going to take a look at the homework from section 2.1.3. And we start with this beautiful little problem from someone who's graphing some lines, right? When Yoshi graphed the lines y equals 2x plus 3 and y equals 2x minus 3, she got the answer shown it right. Okay. One of the lines matches the equation y equals 2x plus 3, and the other matches the line 2x minus 3. Which line matches which equation? Well, if you look at them, right, both of these lines have slopes of 2. In fact, I could pick a couple of points on here, and I could see that the slope pattern is, up 2 over 1, up 2 over 1. And that's true for both of these lines. I'll start here, up 2 over 1. What's different about them is that they have different y-intercepts. This top equation has a y-intercept not at 0, not at 1, not at 2, but at 3, right? This one. So this is the line y equals 2x plus 3, right? 2x plus 3. And this one has a y-intercept at negative 2. This is the line y equals 2x minus 2. So those are the two lines. And we just showed which ones matches. So, and you can see that by when you plug 0 into those functions, right? If I plug 0 into this equation, it gives me 3, hello. And when I plug 0 into this equation, it gives me negative 2. So those are the two lines that I was given. Let's continue. Part B says Yoshi wants to add the line y equals 2x plus 1 to her line. Predict where it would lie and sketch the graph to show its position. Justify your prediction. Well, she just gave me a line with exactly the same slope before, right? It's still this y equals 2x. Every single time x is increasing by 1, this grows by 2. So you can see that it has that slope pattern of y's go up by 2 every single time x goes up by 1, increases by 1. And then she's got this y-intercept of 1. So this line that she's talking about is going to have this as a y-intercept, and it's going to have the exact same matching slope pattern of up 2 minus 1. So I'll just draw this line in here that's parallel to it. So this is where I predict this line will be. And I predict it will be there because when x is 0, this equation produces a y output of 1, right? When x is 0, when this value of x is 0, right, this equation produces an output of 1. All right, so that's part A. Part B. Let's see what part C says. C says, where would the line y equals negative 2x plus 1 lie? Oh, a little different, right? Now, instead of increasing by 2 units each time x goes up by 1, this is going to decrease by 2 units each time x increases by 1. It's still going to have the same intercept as my last function. In fact, let me use a slightly different color. I'll use this green. But I've got this point right here, same y-intercept, but now instead of going up 2 over 1, it's going to go down 2 and over 1. So it's going to go to here, and then down 2 and over 1 to here, down 2 over 1 to here. So this is this new line, y equals negative 2x plus 1. Same y-intercept as her last line, right? But what's different now is now we have this slope pattern of decreasing by 2, and then x every single time x increases by 1, right? So you can see if x increases by 1, y goes down by 2. X goes up by 1, y goes down by 2. So I think that's it for question 30, and we are now rolling on to question 31. The Smallville High School principal is concerned about his school's advanced placement test scores. He wonders if there's a relationship between a student's performance in their class and their AP test scores. So he randomly selects a sample of 10 students who took the AP examinations and compares their final exam scores to their AP scores. So you can see here's, these are students shown like in the column. Like this is a particular student, right? And this first student had an AP score of 5. It's the highest you can get, and they had a 97% on their test. The next person over had an AP score of 1, and which is actually the low. You can't get a 0. I think it's the lowest score you can get, and they got a 70% on the course final. So there's these numbers here. What we're asked to do is we're asked to create a scatter plot on graph paper and to draw a line of best fit that represents this data. Well, if I look at this, I, I need to have AP scores that are like 1, 2, 3, 4, and 5. And then I need to have these percentages. I probably should include like 0%, even though no one had a score that low. But I should scale it up so that I could go all the way up to 100%. So let me take a moment here and just quickly set up um, an appropriate looking graph. Okay, so what I attempted to do was set up an x-axis that could represent my AP scores, and I included 0 there, but these are AP scores, and the smallest you can get is a 1. And then on my y-axis, I've got I've scaled it up to like 100%, so these are their final scores for the course. And what I need to do now to create this scatter plot is I need to plot these values. So I'll do a couple of them together here. So on 5, I have to go to 97. So here's, oh my goodness, 5 and 97, 95, about right here. 1 goes to 70. So here's 1, and this person had 70%. Wow, kind of difficult to hit that. Let me try that again. That's better. And this was supposed to be 97. Let me finish the rest of those. So I basically plotted all of those points. There's not very many. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 of them. And some of them were pretty close to each other on the graph. But one of the things that we observe here when we're looking at this scatter plot is that there appears to be a linear relationship with these two data sets. It appears that the higher their AP score was, the higher their score in the final was. And it's probably the AP score is not driving the final. Probably I should switch the X and Y axis, but I left them like this. But there seems to be some kind of relationship between those. And if I wanted to draw a line of best fit, basically I'm just kind of finding a curve that I think kind of approximates a line that would go through this data completely. And that's not a bad line, so I could just sketch this, right? And this line that I just sketched here, right? It has two properties, right? It's got an apparent y-intercept that's close to 60, and it has a slope. So by looking at this line that I sketched, I could probably come up with a relationship that I might be able to use to predict what their score in their final was if I knew their AP score, or I could use it to predict an AP score if maybe I knew their score on the final. We're going to do a lot with this year, and by the time we finish the year, we're not going to just be sketching these, but we'll definitely know how to come up with the least square regression line, and we'll have a pretty good idea of what that line, how we get it, and what it does for us. So let's move on to question 32. But that's what I wanted you to do here, and they're going to ask you to do this several times. So just set up the XY axis, plot your data points, and then sketch a line that appears to fit the data. And then it does say down below, it says use your line of best fit to predict the final exam score of another Smallville student who scored a 3 on their AP test. Oh, so I guess they did want it to go from AP to final. So if I had another student who scored a 3, right here down here off the screen, this is the 3. So if I come up here and I bring this in, I would say a student, that scored a 3 on the test is probably going to be getting, between like 75 and 80% just based on this set. So it's my prediction. It is a pretty small data set. They did say it was randomly selected, but I wouldn't put a lot on that, a lot of faith in this model, but it is a model and it does attempt to make a prediction there. Let's move on to question number 32. 32 says compute each product, write the final answer in scientific notation. So I don't have to use a lot of, I don't think I need to use a calculator here. I'm just going to rewrite this. In this first one, I am multiplying a 6, and then there's times a 4, and then I'm going to be multiplying it by 10, two factors of 10 and 5 more factors of 10, right? 2 and 5. So there's a total of 7 factors of 10. Now, this number that I'm writing here, right, 24 times 10 to the 7th is not scientific notation. In order for it to be in scientific notation, right, I have to have a number that is between, it has to be greater than 1 but less than 10. So I need to move my decimal point to here. It has to be 2.4. Now, you're probably saying to yourself, well, you can't, it's 24. You can't just change that. You can't just change it to 2.4. But here's the magic, right? If I take 2.4 and I multiply that by 10, right? Understand that this thing right here, that's just the number 24, right? It's just 24. 2.4 times 10 is 24. And this is the number 24. What I have to do now is I just have to multiply by the 10 factors of 10. So 7 factors of 10 times 10 to the 7th. And then I can simplify this. So I've got a single factor of 10 and 7 more factors of 10. So what we're looking at here is a 2.4. And I'm just going to multiply that by 10 to the 8th power. So this is my answer, and it is written in scientific notation. And I didn't use a calculator, did I? No, I didn't. Let's try this next one here. So this next one, I might use a calculator. I am going to multiply the whoops, let me get that right, 1.75, and I'm going to multiply that by 8. And then you can see that's being multiplied by 10 to the negative second, and then times 10 to the negative 8th. So negative second, negative 8, that's 10 to the negative 10th. So times 10 to the negative 10th power. And remember, each one of those powers of 10, like 10 negative to the negative power of 10, we're dividing by 10, right? So 10 to the negative 1 is 1/10. So that's like 1/10 times 1/10 times 1/10. I could say that 10 times. That's what's going on there. So now we need to multiply those numbers. So the 1.75 times 8 is 14. So this is going to become 14 times 10 to the negative 10th power. The problem with that is not scientific notation, right? So what I'm going to do instead is I'm going to take the number 14 and I'm going to write it as 1.4 times 10 to the positive 1 power, right? So this is exactly equal to the 14. That's 1.4 times 10. But I've got to bring over the fact that I'm multiplying this by 10 to the whoops, I've already got the x there, or multiplication symbol, times 10 to the negative 10th. So now let's just clean this up, right? I've got 10 to the positive first and 10 to the negative 10th. So that's going to give me 1.4 times 10 to the negative 9th power. There we go. That's it. That's it in scientific notation. Moving down to the third one here. Oh, a little division problem. So I do have the 9 divided by 4, and 4 goes in there twice, and there's some left over. But if I was to do that and look at it as a decimal, it's like 2 and a quarter. So this 9 divided by 4 becomes 2.25. Well, guess what? That would be appropriate for scientific notation. So I'm not going to need to adjust this one. Times. Now, I've got in my numerator 10 to the 5th, and in my denominator I've got 10 to the 7th. That's going to be 1 over 10 squared, which is 10 to the negative 2nd power, right? So, and you know, the shortcut method that we looked at with the laws of exponents, this is going to be 10 to the 5 minus 7 power, which is still 10 to the negative 2nd power. So I've got 2.25 times 10 to the negative 2nd power, and that is scientific notation. So that's my answer to part C. Let's move on to question 33. 33 says, rewrite each of the expressions below in a simpler form. Your new expression should not contain negative exponents. Okay, so let's look at A first. Let's see, there's a 5, and I'm multiplying that times a negative 3. So this is going to be a negative 15. And you'll notice that the 5 is not being raised to the third power, and that negative 3 is not being raised to the negative second. So it's just 5 times negative 3, which is negative 15. And then we've got x to the third and x to the negative second power. And when we simplify that, right, that's I can use the law of exponent, right? 3 plus negative 2 is just 1. So this is just negative 15 times x. So that's it, and we're done with it. Or I could take a little bit more scenic route and say, oh, x to the third times 1 over x squared. I could do that if I'm, maybe you have. I don't have anything to get to, so I can do that. So I can rewrite that as x to the third over x squared, which is still x, but you can see I end up in the exact same spot. So the answer is negative 15x. Let's move on to B. Okay, so B, I do have 3 of these things, right? I have 3 4p squared q, 4p squared q, 4p squared q. Now, if there were 20 of them, I would not be doing it this way. I would be looking at the shortcut. But right now, as I write it out, I'm trying to develop and make sure I understand a possible shortcut. So you can see when I have 4 and I'm raising this whole thing up to the third power, I end up getting 1, 2, 3 factors of 4. So I can write that as 4 to the third. And when I have the p squared and I was cubing that, I end up getting 1, 2, 3, 4, 5, 6. I get p to the 6th power. And coincidence? 2 times 3 is 6. That's nice. And the other thing I've got is 3 factors of q. So q, q, q. So q to the 3rd power. So I could leave it there, but I probably would just go ahead and take the 4 and multiply out 3 factors of 4 and get the number 64. So I'd probably finish this off as 64 p to the 6th q to the 3rd. And honestly, I may not do that. If I'm concerned that I could be looking for common factors again later, or combining this with some other things, I might leave it in the form 4 to the 3rd because it's easier for me to manipulate. All right, last one, part C. Here's our opportunity. We get to multiply. I'm going to multiply by a giant 1 in the form m to the 1st, right? M to the 1st over m to the 1st. And I selected that specifically because I want to neutralize this negative exponent in my denominator. Now, it is multiplication of fractions, and when I look at my denominator times my denominator, right, m to the negative 1st times m to the 1st, right, that becomes m to the 0 power. So this is going to become m to the 0 power. And what's significant about that is that's just the number 1. So I'm dividing by 1 now in my new answer. And then my numerator, I've got 3, right? There's a 3. And then there's 7 factors of m. And there's an additional factor of m that I got when I neutralized the m to the negative 1 below. So I have a total of 8 factors of m. So I just write 3m to the 8th, 3m to the 8th. And there's no reason why I keep this over 1. So I could just write it as 3m to the 8th power. And I hope you're seeing that perhaps there's even some other things we can do, right, to manipulate and some other possible shortcuts. But that's our answer there. It's 3m to the 8th power. Right? Let's move to 34. It says, which graphs below have a domain of all real numbers? Which have a range of all real numbers? Which are functions? And there's just 3. There's A, B, and C. And when I look at A, these arrows, right, indicate that this is going to continue going in this direction, continue going in this direction. And the way these are slanted, I mean, it looks like it could take a while, but pretty much any value that I pick, even way over here, value that I pick for x, there's going to be something way up there where it's going to hit this curve. So even though I might have to draw this curve a lot or extend it a lot, there's going to be a value there. So to me, looking at this, the domain of this is all reals. So which graphs have a domain of all real functions? So I'm going to say domain of all reals. I would say A has a domain of all reals. I would also say that B has a domain of all reals, right? Because there's it doesn't look great on the screen, but there's arrows here, so they continue in this fashion, and eventually any value of x that I pick is going to have an appropriate output value for it. So A and B. And there is C down here. C does not have a domain of all reals, does it? Because you can see the smallest value in C's domain is like the number -2, right? So C, I would not say its domain is all reals, but A and B have domains of all reals. Now, the other thing it says, which have a range of all reals. So let's write that down. Range of all reals. And I would say a range of all reals. A has a range of all reals because it's going to encompass all these positive values going this way and all the negative ones shooting down here. So all reals for A. B, not so much, right? B's range is limited. The largest value I can get appears to be right here, right when y is 5. So my largest range value for B is 5, and then it's everything below that because these arrows keep shooting down. And for C, it looks like C has a range of all reals, right? It doesn't appear that it's going crazy fast, but eventually the way this curve is working, I don't have to exaggerate even more than it is, but eventually the way this curve's working, it's going to keep going up. And I don't mean to be cheating. I'm trying to push it. I don't want to push it up. They're not asymptotes. It's going to continue off and keep growing like that. So I would say C has a range of all reals. And then the final question is, which one of these functions, well, which ones of these relationships appear to be functions? And I think you guys know, right? The only one, it's pretty clear that A and B, right? For every single value in the domain of A and B, there's exactly one output, right? So the domain values have exactly one output. When I say exactly one, well, it doesn't mean it can have 2 or 3 or 4, right? It has exactly one, no more than one. C, on the other hand, it looks like for almost all of the domain, all of those domain values have 2 outputs that we can see, right? Except for maybe -2. It looks like at -2, there's a single output of maybe 1, but that's the only domain value that has a single output. Everything else has more than one. So in order for a relationship to be a function, right, each valid member of the domain can have no more than one output value, right? The moment they have more than one output value, it's not consistent and predictable because I don't know what's the appropriate output value, right? If, for example, this one at 4 could be like, well, maybe here let's say at 1, it could either be -1, or at 1 it could be, I don't know, maybe 2.5, right? Probably not 2.5, but for 1 it could be either one of those. I don't know which one it's going to be, so it's not consistent, not predictable. Each member of the domain may only have, right, may have no more than one output value. All right, and I think that's our last question. Oh, where'd the time go? Anyways, this is Mr. Roberts. Have a good evening.